Hi there. This is a little lesson on scalars and vectors, which are different types of quantities that we run into throughout physics. For our class, that's going to be really the step one in this unit. Our opening unit in Physics 1 is kinematics. And in kinematics, we're going to encounter things that are vectors. So we might as well go ahead and get that under our belt. What is a vector? And that will be the purpose of this lesson. You should be able to understand what is a vector, how do we give the value of a vector, and those are key concepts for this lesson. In the set of objectives for this unit, it's objective number 1. Notice there's not any specific homework for this, but you get lots of practice with vectors throughout physics. So let's get to it. Scalars versus vectors. We'll start with scalars. If you've never heard of this idea, you're nonetheless familiar with scalars, no doubt. A scalar is a name for a quantity that only has a magnitude. The word scalar is kind of interesting to me, so why do we even have a name for this? In a way, we have this name, at least seems like to me that we have this name because we have a thing called a vector. Well, we need a name for the other thing. So a scalar is basically just a numerical value, which usually includes units. This says may include units, but often includes units. And we're just describing some quantity, some aspect of the universe that we want to put into a numerical value. And all we need is a single numerical value. And that's a complete description of this quantity, whatever it might be. We're going to look at some examples in just a second. But if somebody said, well, how old are you? And you said, I'm 16 years old. Well, that would be an example of a scalar because you have answered the question with a single numerical value. A vector is not a single numerical value, and that implies it's more than that, which it is. A vector is a quantity that has kind of a two-part aspect to it. It has not only a magnitude or size, of course the word magnitude basically means size, but a vector has a direction. So if you're trying to describe a vector, you need two pieces of information. And those two pieces of information will describe how large this quantity is, that's the magnitude, and then some sort of indicator of direction, something that tells us what is the direction of this thing, whatever it might be. So there are many vectors in physics, but you may not have used vectors or talked about vectors in other classes. You may have used vectors in other classes, but sometimes you may not have really stressed what is a vector. So we're going to look at some examples of vectors here in just a minute. In fact, we'll just go ahead and jump to that. I have some examples we're going to look at, and we're just going to make a set of examples. We'll throw it into one of two columns. So we'll play a little game here, and you can you can pause the video if you want and try and figure out where is this going to go. So if we threw out the word mass and we said, should this be a scalar or a vector? Not should it, is it? What is mass? Well, mass is something that can be scaled. How would you measure a mass? You might use a scale. The word scalar, I believe, comes from the word scale. So that which can be scaled is a scalar. And mass is an example of a scalar. The mass of an object, I might say, this object is 5 kilograms, and that's it. That's all I need to say. Single positive value that describes the mass of an object. How about volume? Volume. How do I measure volume? Well, in chemistry, you might measure volume with a graduated cylinder or a beaker that has gradations on the side, like this one in the picture. So 100 milliliters would be the full beaker, but it looks like there's only 40 milliliters in this container, but that's it. Once again, there's a scale. Once again, there's a single numerical value, another example of a scalar. As I said a moment ago, you're probably familiar with scalars. Scalars are all around us. You just might not know that they're called scalars. The length, I have here a picture. Suppose I'm measuring the length of this $5 bill for some reason, and I find, oh, it's 15 centimeters long. Have you ever heard a ruler called a scale? Sometimes people just say, hand me that scale, that's a ruler. And yep, that's another scalar, something that can be scaled, something that has a size, doesn't have a direction. Sometimes there might be kind of a directional aspect, like the length is usually the long part, and I can tell but it's not really a defined direction, so that would still be a scalar. What about force? So now let's look at this quantity. This is one we study in physics. We spend a lot of time talking about forces in physics. I have a picture here, and there's a hook in this picture. I'll activate my little pointer here. So I've got a hook, and this hook is pulling on this metal cylinder down here. That's a 1 kilogram mass. And the hook is connected to this spring scale. In fact, there's a spring inside here that's stretched. And we're measuring the force by doing that. So when I look at that picture, I hope it makes sense to you that the force would be a certain amount. So here I can find on the scale how many newtons is that. And that would be 5 or 6 newtons according to the scale. But there's also obviously a direction. The hook is pulling on the kilogram in a certain direction. The direction that it's tilted. The spring is tight, stretched tight, so there's a pull here. Anytime you push or pull something, it's got a direction, whether you like it or not. If I push a table, I might be pushing it to the east, or I might be pushing it to the west. I could push it down, or I could pull it up. But it has a very specific direction I could point in, and that makes it a vector. So this is a quintessential example of something that we can call a vector, properly should be called a vector. It is a vector, whether we like it or not. It is a quantity, a phenomenon in the universe that definitely has an intrinsic direction that I can point in. Temperature. What about temperature? Temperature might have a direction of change. Oh, the temperature is going to go up, or the temperature is going to go down. But if you think about measuring temperature, if you say it's going to go up, it's not a literal up, right? I'm not actually going upward. It's just increasing. A more proper way to say it would be to say the temperature is going to increase today. So once again, this would be a scalar. Temperature can be negative, but a negative quantity can still be a scalar. Temperature can go up or down, but that doesn't really change anything that we're interested in. So we'll keep going here. How about time? Forward or backwards in time? We only go forward in time. But can you point in the direction of time? Time is sometimes thought of as a dimension in a way in physics, but time is also a scalar. We could say we're going forward in time, but that doesn't mean that the end of this video is that way, right? Or this way, or I can't point to the end of this video. Forward in time is just the way we say it. Now, velocity is something that we study in physics. So I have an example of velocity from a weather report. So here's a little screen clip. And notice this is a weather forecast, and it shows a wind forecast of 6 miles per hour north-northeast. And if you think about the phenomenon of wind, wind has a strength, that's its magnitude or a size. How strong is the wind? But it definitely has a direction. Wind has to blow in some direction. If the wind is blowing, it's definitely blowing in some direction. So here we go again. That's an intrinsic quality of the wind. It has an inherent direction. So whether you like it or not, if we're trying to describe the wind completely, if we want a complete description of the wind, we need to give the magnitude and the direction. So we can visualize it as an arrow, and there was a little indicator from the screenshot pointing in this direction, north, showing the north-northeast wind. Oh, you might be a little surprised here. North-northeast, does that arrow look right to you? Perhaps the answer depends on your familiarity with meteorology. We'll talk about that in just a second. But anyway, this would be a vector because it definitely has a direction. So let's put velocity in the vector column. So notice we have only a couple of vectors, and there are way more scalars than vectors, it seems like. There's an important handful of vectors that we get into in physics, and there are several in this first unit on kinematics. So we just want to be familiar, and the way we work with vectors is different than the way we work with scalars. So that's why we need to know the difference. If we go back to that wind example, let's get a map view. So here's kind of a map view of Knoxville, and it's oriented the way we always do, right? North up, south down, east and west. And if we think about this wind, it was described as north-northeast. You might not be familiar with this, but on the weather report in meteorology, when they say north-northeast, that means the wind is coming from the north-northeast, which means it would be blowing toward south-southwest. Why do they do that? Well, they do that because that's the way a weather vane works. So a weather vane points into the wind. So if you had a weather vane on top of your barn, or at a weather station, the little, you've seen it before, it'll turn the way the wind is blowing. It's going to point into the wind. So that's the way the weather vane would be pointing, but it means the wind is blowing in the opposite direction. Now in physics, we don't do that. We don't say which way a vector is coming from. We say which way a vector is pointing towards. So my example is clearly a vector. The weather report, they give you a vector when they describe the wind. There is a magnitude and there's a direction, but they don't give a direction angle. So the way we often do this in physics is we give a two-part quantity for a vector. There's a magnitude, and that's pretty much like a scalar. It's just an amount, it's a number, it probably has units, typically has units. But then we use this idea of a direction angle. So this is a very important idea to be familiar with this. Many materials you see in physics will have a direction described by an angle. And you probably have seen this somewhere before. A direction angle specifies which way the vector is pointing toward, and the way we determine it most often, and this is similar to what you often do in a math class with angles, is we're going to start and move counterclockwise, starting at a line that's horizontal and pointing to the right or east. So pay close attention to that statement. That's actually a pretty important one that you don't want to get confused about. And we're going to look at some examples with the rest of this video. We're going to illustrate this idea about the direction angle. Let's go back to our wind. So in physics, we would not describe the wind in this manner. What would we typically do in physics? Well, we're going to imagine a line extending to the right, or in this case, east, from our vector's tail. The tail is not the pointy end. The pointy end would typically be described as the head of the vector. The other end is the tail. And then form an angle going counterclockwise. So watch the animation as I put this into motion. So here comes an angle counterclockwise, starting at this imaginary line that we added. And that angle, if the wind was a north-northeast wind, according to the weatherman, in physics terms, we might say, oh, that's a direction 247.5 degrees. A very specific angle can be used to describe that. Where did that angle come from? I hope you could figure it out. It is a precise value based on what exactly south-southwest would be. Southwest is halfway between west and south. And then halfway between southwest and south would be south-southwest. That's what that means. So I can do a little figuring. I've got the math shown here. We're basically taking 180, and I'll use the pointer here to try and illustrate this. So if you go from east and swing around to west, that would be 180 degrees. Keep going halfway to south, that would be another 45. And then halfway from there to south, halfway from southwest to south would be half of 45 again. That's where that angle is coming from. So this would be our direction angle. And then 6 miles per hour would be a description of the magnitude. And then we would write it in the following way. So how would we typically write a vector in physics? Like this. The velocity v, and notice there's a little arrow symbol on top of the v. And that little symbol indicates that this quantity v is a vector, so that's a common notation for vectors. So the velocity is 6 miles per hour, magnitude first, and then comma, direction, 250 degrees. I rounded it off a little bit, just significant digits. We didn't have very precise information, so we're just going to call it roughly 250 degrees to the nearest 10 degrees. So here's our final answer in physics terms, the way we would describe the velocity of the wind, the way it is blowing toward. You might have been bothered by the fact that this arrow was not centered in this diagram, but I did that on purpose. In physics terms, that vector would be the same wherever it is on the map in this case, or wherever it is located. We can imagine kind of picking it up and moving it around. That velocity vector would be the same anywhere. And if the wind were blowing, the velocity might be essentially the same over a wide span. But it would be the same description no matter where that vector is located. It does not have to be starting at an origin for this to be a correct description of the vector. I have some other vectors we're just going to take a quick glance at. So here's a vector A. Notice the symbol, the arrow symbol. I see AOA is a vector. I have a diagram of it, and you just want to visualize a vector as something that could be illustrated with an arrow. Would be another way to describe what is a vector. When we draw the arrow, we typically make the length equate with the magnitude or draw it in proportion to the magnitude, and then of course the angle is going to be measured always the same way. So we want to be consistent with the angles, always this imaginary line. I don't have to draw the imaginary line, but I added it here so you can see the logic in that. Let's look at another example. Here's a vector B. 6 meters per second, 270 degrees would be a velocity vector, kind of like our wind example. The vector B has a magnitude 6 meters per second, but I could draw it 6 units long if I want to illustrate it graphically. And then the 270, do you see where that's coming from? Imagine it. Can you see that angle in your mind's eye? Try it right now. Here it is. Here's another vector, vector C. 7.5 miles, 160 degrees. 160 is almost 180, so almost opposite of pointing to the right would be pointing to the left, except not quite left. Didn't make it quite that far, going counterclockwise. And I'm just trying to show you some examples of what these angles look like. Now, in practical terms, in physics, we typically have problems involving either motion in a vertical plane, such as you kicked a football. The football follows a path that would be in a vertical plane. And while it's moving, you might describe the football as moving to the right, or moving up, or moving left, or moving down. We're going to see those kinds of directions very frequently. In fact, you could use that as part of your answer. If a vector is only pointing up, you might just give the direction as up instead of an angle. But in terms of our angle system, those angles would be to the right equates with 0 degrees, and then going counterclockwise from there, pointing up would be 90 degrees, pointing left would be 180 degrees, and so on. So the football might be falling down, and then you have an answer that's a vector with 270 degrees associated with that vector. Or you could just say down. Here I have a photograph, kind of a cool stop-action photograph of a tennis serve. So let's imagine describing the velocity of the tennis ball. So here comes the tennis ball. I've tossed it up, and now I'm getting ready to hit it, but it's moving down at an angle at 0.6 meters per second. What would that angle be estimated in your mind's eye right now? How about the velocity once it's hit? So once I hit it, it's essentially moving horizontally at a really high rate of speed, 45 meters per second. Estimate these angles, and I've provided the main angle, so to speak, that you can look at for comparison. Did you estimate something like this? These angles would be very close to the following. As the ball is falling down, but moving diagonally, we might say its velocity is towards 305 degrees, and then once I hit it, its velocity is towards 0 degrees. Sometimes we have a different view. Sometimes we have motion within a horizontal plane. So you might have a car traveling down a road, or say a ball rolling around on a table. The ball might be rolling to the east on the table, or it might be rolling to the west on the table. So that would be motion that's occurring in a different plane, but we can use the same ideas. So east, north, west, and south would become 0, 90, 180, and 270. Here's a satellite view of our school, Farragut High School, and same angles could be used to describe something happening in this view. So if you're walking around in Farragut High School, you might be moving in a plane, and you might be moving east or south or west or whatever. So here's a little problem for you, a little mystery of sorts. So a student walks 150 feet, 177 degrees down a hall. Which one would that be? There's really only one answer that makes sense at Farragut High School. So if you look at that direction, 177 degrees, that's really close to east. And there's only one wing or one hall that makes sense. We have this wing kind of sticking off to the left, almost to the left, but not quite. So I hope that you have picked this wing over here. That would be an example of a vector quantity describing how much a student moved. 150 feet, 177 degrees. Tells us not only how much they moved, but the direction that they moved, nearly east. That's the red wing, or I think they call it the Narnia wing these days at Farragut High School. Lastly, I have one other thing to say about vectors. If you look at a compass, you will see a different set of angles. So here's a compass that is pointing towards northeast, pretty close. So what would that angle be? Well, on a compass, for us, it would be 63, like our scheme of doing things. We're going to start over here at east and go counterclockwise. But on a compass, notice it's 0, that'd be like 27 degrees. If I were pointing the other way, on the compass it would be 207 degrees or something like that. But in our scheme, it's 243 because we're going the other way. So watch out for that. Navigators, pilots, somebody using a compass might use a different set of angles. So there are different systems that can be used. The most common mathematical one, the most common physics one is the one that we're using, where we have 0 starting at east and going counterclockwise. On a compass, you have angles that start at north and go clockwise. Those are usually referred to as bearings or headings, something like that. And that would be okay, if you describe a vector that way, you might want to be a little more specific and use those words, bearing 27 or compass heading 27 degrees, or you can even just describe it in words. 27 degrees east of north would be a common description of that direction outside of physics, or even in physics. I mean, it's okay. There are different ways that you can specify the direction of a vector, so keep that in mind. But our default, what we're typically going to use in physics, is the one that's been described previously in the video.